So we're going to continue looking at Chapter 1 with the second part of our lecture. And we're going to begin this little video with a couple of more definitions. Now, I mentioned in the last video how important it is that you learn the definitions of things. You're going to be tested on definitions of things. You need to know how things are defined. If you don't know what the words mean, you don't know what you're talking about, right? So please put some effort into learning these definitions. I suggested flashcards. However you learn definitions, just make sure that you do learn them. Now, the two definitions that we're going to talk about in this video, in this slide, are scalar and vector. And the reason that we have these two definitions is because in nature, we find that some quantities have a built-in direction. Other things do not have a built-in direction. And so we categorize them according to whether or not they do. So a quantity that does not have a built-in direction, without a built-in direction, we call those quantities scalar. So one example of a scalar quantity is temperature. Temperature does not have a built-in direction to it. So if I asked you what the temperature in the room was, you would say something like it's 72 degrees Fahrenheit. You wouldn't say it's 72 degrees Fahrenheit to the left. You know, it doesn't make any sense to say that temperature has a direction. Now, some quantities do have a direction built in. An example of that would be a force. Now, what does it mean that the force has a built-in direction? Well, you can see in my picture here, I've drawn a box or something that someone's pushing with a force, and that force is pushing to the right. The direction in which the force is pushing matters, because if I push from the other direction, the box is going to slide in a different way. And so the direction that you apply a force in absolutely matters. So force is an example of what we call a vector quantity. It's something that has a built-in direction. The direction matters. Now, what happens if you have multiple forces acting on something at the same time? When you have multiple forces acting on something at the same time, we have to think about something called the net force. And the net force is simply the total force compared to all the individual forces. So we can see in this picture, at the top I've got a block here, and there are two 5-Newton forces. In other words, imagine that there were two ropes here. You and I are trying to pull this crate across the floor, and each of us is pulling with 5 newtons. That is completely equivalent to having one rope with one person pulling with 10 newtons in the same direction. And so two 5-Newton forces to the right add together to give a 10-Newton force to the right, and these are completely equivalent to one another. So if you have multiple forces, you can simply add them up to get the net force, or you might think of it as the total force. That's what net force means. Now there's something that's a little bit tricky here. If I have a 5-Newton force acting to the right and an additional 5-Newton force acting to the left, those two forces will actually cancel, and it's completely equivalent to having no forces at all. And so in this sense, we tend to say that forces that are pulling or pushing to the left are negative, whereas forces that are pulling or pushing to the right are positive. So this guy would be positive 5 newtons minus 5 newtons because it's to the left. So positive 5 minus 5 equals 0. And so the net force is 0. Now over here in the third one, can you see why if I've got a 10-Newton force here and a 5-Newton force there in the opposite direction, that's going to be an equivalent net force of 5 newtons to the right? Here we have 10 newtons, which is positive because it's pointing to the right. Here we have 5 newtons, which is negative because it's pointing to the left. 10 minus 5 leaves you with 5. And of course, it's not just 5 newtons. If you say 5 newtons, that's wrong. It's 5 newtons to the right, because force is something where the direction absolutely matters. Now, in your textbook, they discuss something called the equilibrium rule. And the equilibrium rule is represented by this equation. Now, there's this weird symbol here. You may have seen this before in your math classes, but if you haven't, this is the capital Greek letter sigma. And in mathematics, sigma represents summation. And so this means add up, F stands for force, and so this says add up all the forces and you get 0. That's the condition necessary for something to be in equilibrium. If you add up all the forces, you get 0. Another way of saying that is for something to be in equilibrium, the net force is equal to 0. And so that's the necessary condition for something to be in equilibrium. The net force is equal to 0. Now, that's kind of abstract. What does that mean in practice? So this is a nice example from your textbook. You have this scaffolding here. You have a couple of guys here. Maybe they're painters or window washers or something like that. And this platform on which these guys are standing is balanced. It's in equilibrium. It's not going up or down. It's not falling or it's just standing there, sitting there. And if that's true, we know that for something in equilibrium like that the net force, the sum of the forces, must equal to 0. And so what does that mean? Well, we've got this force is going up and this force is going up. We tend to call forces going up positive, just like forces to the right are positive. And then these forces are going down. And forces that are pointing down, we tend to call negative. So what are these forces? Well, you've got these two ropes attached to the platform. And so there's a force in the rope that is, we would call the tension in the rope, and that's pulling the platform upward. But then you have the weights. You have the weight of this person pulling down. You have the weight of this person pulling down. And you have the weight of the platform itself pulling down as well. So these three things, the two people in the platform, their weights are all pulling down. And so those weights are in the negative direction. And then you have the two tensions in the two ropes. Those are in the positive direction. And so this one plus this one minus that one minus that one minus that one, if you add them all up, you get 0. That's what it means to be in equilibrium. And just to throw in a little something extra, this is an example of what's called static equilibrium. Static means stationary. The object's not moving at all. It turns out if this platform were being lowered or raised at a constant speed, the condition for equilibrium would still be true, but we would call that dynamic equilibrium because it's moving. Don't worry about that yet, but I just wanted to throw it in there for completeness. The main thing you need to get from this slide, though, is the idea that if something is stationary, all the forces acting on it have to add up and give you 0. And you've got, again, positive forces and negative forces. You add them all up, you get 0. Now, when talking about forces, you have to understand where all the forces are. And if you are just sitting on the ground, or for example, if I have a box on the ground, that box has a weight. And remember, weight is the force of gravity pulling it down. So that weight is pulling the box into the ground. Why doesn't the box crash through the ground? It's because the ground must push back with some other force. And what's true about these forces? They have to add up to be 0 because the box isn't flying off the floor or crashing through the floor. It's stationary. And so we know from our equilibrium rule that these forces have to add up in balance. And so this is called the support force. Right here is the support force, and this is the weight. Now, there are a couple of nice images from your textbook that illustrate this principle. And one of the things that's kind of neat, if you stand on a bathroom scale, the bathroom scale actually isn't measuring your weight. That would be the force of gravity. What it's measuring is the support force. And we know that those two things in general are going to be equal. But imagine if someone came up behind you and pushed down on your shoulders. What's going to happen to the reading on the scale? obviously it's going to go up because it would read the amount of weight that you have plus the amount of force that someone was pushing down on your shoulders with. And so the support force has to balance all the forces pushing down into the ground. And so that's what the scale actually reads. It's the support force. And in general, the support force is always going to push back as hard as you push into the surface with. And so here we have a book that's pushing down onto this table or whatever. Someone's pushing down on a spring. The support force is always going to match the force that's being pushed down with. Now, we've already talked about friction a little bit, and I want to be a little bit more specific with our definitions. Now, this is kind of a complex definition here. Friction is a force that resists the relative sliding motion of solid surfaces and or fluid layers moving relative to one another. Now that's complicated and fancy sounding, but all it really means is that if you've got two things moving relative to one another, there's going to be friction between them. So for example, if I have a box and that box is sliding along the floor, the bottom of the box is sliding relative to the floor. They're moving relative to one another. It's sliding across the floor, and so there's going to be friction. If I have a boat in water, the water is sliding across the sides of the boat. That's going to create also a kind of friction. And same thing with air resistance also. If you stick your hand out your car window when the car is moving, you feel the air resistance against your hand. It's applying a force against your hand. And so that's analogous to the force of friction. Now, friction involving liquids and gases is a little bit more complicated. So we're going to start by just considering two solids moving relative to one another, like a block sliding across the table or the floor or something like that. So here are some interesting facts about friction. So friction is always opposite the direction of the motion. So if this block is being pulled to the right, the friction is going to be to the left. Whichever way the block is moving or wants to move, the friction is going to be in the opposite direction. Now, if you've ever pushed anything heavy like a couch or a refrigerator, you've probably experienced that it's really hard to get it going, but once you start to slide, it's easier to get going and keep going. And so here's basically what happens. So you're pulling on the refrigerator, say you're trying to move the refrigerator, and you're pulling on it, and it's not moving, so you pull harder. It's still not moving, you pull harder still, and eventually it starts to slide. As you increase the force, there's some threshold value of force that's necessary to get it to start moving. Once it gets moving, though, the amount of friction is reduced. And so there's actually two kinds of friction. There's the friction before it starts moving and the friction after it starts moving. And the friction before it starts moving is always bigger. Now on this slide, imagine that we're pulling to the right, and so this block is going to be sliding across the floor to the right, and the friction is obviously going to be to the left. Now imagine that there's another force pushing it into the ground. Guess what's going to happen to the friction? It's going to get bigger. And so that's one of the things that determines how much friction you have. Friction depends on the amount of force pushing the two objects together, the two surfaces together. I wrote that out for you here because it's a really important idea. So normally, if this box is just sitting here, what's pushing the box into the ground is just its weight. And so the friction is going to depend on how heavy the box is. But if I come and push down from the top, I'm just like in the previous example where the bathroom scale went up, the amount of friction is going to go up as well, because friction depends on how hard the surfaces are being pressed together. That's one of the two things that matters for friction. The other thing that matters for friction is how rough the surfaces are. Rougher surfaces lead to more friction. And so here I have an image of a box sitting on a table or something like that. If you were to zoom in with a microscope or something, The box to the naked eye might seem very smooth, the tabletop might seem very smooth, but if you zoomed in with the microscope, you'd find, if you zoomed in enough, you'd see there's actually roughness at the microscopic level between these two surfaces. And these roughnesses create little hills and valleys, little nooks and crannies that get caught up in one another. And so, for example, you can see right here, if I want to slide this guy to the right, well, I've got to push this guy in such a way that it climbs up over the hill of this little nook and cranny here, and that creates the resistance to the motion in the opposite direction. And all these little nooks and crannies, they sort of interlock with one another. This explains why the friction increases if you push down on it, because if you push down on something, you're pushing these little nooks and crannies closer together, and it gets harder for them to climb up the hills. It also coincidentally explains how lubrication works. If I were to put some oil in between here, that oil, the top object would actually float on that oil, and the oil would keep it from sinking deeper into these nooks and crannies, and that would reduce the friction. But the main takeaway here is that friction depends on two things. It depends on how rough the surfaces are and how hard they're being pressed together. And remember, friction is about the motion of one sliding relative to the other.